Hi, good evening. This is Tariq Rashid, Physiologic Part 2. As promised, this is a tutorial part on physiologic. I'll go through the tutorial part. Today's class is about tip calculator. In a restaurant, tipping system can be designed or can be systemized and use physiologic to do this system. Let's say we have, just for the sake of learning, the system has two inputs. So input 1 and input 2. First one is service, and the second one is food quality. Food quality and service quality, SQ. Two inputs you have, SQ, service quality, and food quality. Then these are the inputs. The output is tip percentage. Okay? So here we have service quality. We need to know the edges. We have poor, good, excellent. Likewise, for food quality, we have bad, decent, great. And the rate for service quality is 0 to 10, whereas the rate for food quality is 0 to 10 as well. Now, for tip percentage, 0 to 25%, that's the percentage of the tips. Cheap would be 5%, average would be 13%, generous 25%. So that's how we put the system. Now, diffuzzification, degrees of membership, we are trying to get the inputs and we project this inputs onto the membership functions, and then we will try to see which hedge has a degree in that variable. So assume that service was 4 and food was 8. Okay, we have two crisp inputs, and we try to find the tip. So x1 is 4. So we try to, and then x2 is 0.8. So if we are going to project 4 service, this is service quality. So if we project 4 on this line, it will have 0.2 poor, and if you go further up, it will be 0.8, roughly 0.8 good. Green is good. So green is good, and poor is red. Now, and it does not hit the blue color, so excellent is 0. That is we get. So poor is 0.2 and good is 0.8, and excellent, because we didn't hit it. When we did the projection, we didn't hit the blue color as in here. So we didn't hit it from 4. We just hit this line in here and hit this line in here. So excellent is 0. Now, for our input for food is x2.8.0. So if I go to food quality, x2 is 8. So I project 8 here. I hit this and I hit this. So it hits the green decent. It will be, if I project it here to, that's I think 0.4, and the blue 0.6. So it will be 0.6 great and 0.4 decent. Let's see. 0.4 decent and 0.6 great membership function. But the bad, we didn't hit the bad. So we didn't hit the bad. So nothing. The bad is red. So this one didn't hit it. So when you project from here, it just hits this 2 line. It doesn't hit the red one. So that's why I gave 0 to there. Now, this is easier now, the job. We need to create rules. Now, we did the membership functions. We create the rules. Now, let's go with the case A, which is two rules we have in the system. And we perform diffuzzification using average weight. And then after that, we use three rule systems. Let's do the two rules. Okay, two rules. Rule one, if service is good and food is great, then tips is generous. So tips, we say that tips generous, that's 25. So service is good and food is great. So we have for the service, if I go back to here, for the service, I have good, that's 0.8, service good, and food is great. Let's go see the great, how much great. Food is great, 0.6. So 0.6 and 0.8. For service, 0.8, this one, good. And for food is great. So for food is this one. So 0.8 and 0.6. Now, because the rule says and, that's and, so take minimum of them. The minimum of them, 0.6. That's done. Rule 2, if food is good, if service is good, again, 0.8. And food is decent. When food is decent, 0.4. So 0.8, again, 0.8 here for second rule, 0.8. And food is decent, 0.4. So because there's and between them, then we take 0.4. Let's check. So the service is good and food is decent. So we take 0.4. And the tip is average 13. We say tip is average 13. The bad is 0.5 and the generous 25. So these are the rules that we made it. Now we do diffuzzification. Diffuzzification sigma of W multiplied by S sub I, W sub I over sigma or sum of W sub I. This is the singleton output value, and this is the firing strength of the rule. Now here we have 0.6 multiplied by 2.25 plus 0.4 multiplied by 0.13. That's the rule. We have, if we go to here, that is the percentage. Okay, so percentage, we have 0.6 and we have 0.4. So 0.6 multiplied by 25, because that's the first rule, and 0.4 multiplied by 13 plus the weighted average, 0.6 plus 0.4. And now we will have the tip is 20%, 0.2. The tips is 20%, 0.2. Now, if we add another rule, which is service is good and food is great, 0.8 and 0.6, we take the minimum of them. The service is good and food is decent. Again, we take minimum of them. So this is 0.6 multiplied by 0.25, and this 0.4 multiplied by 13.13. And service is food, service is poor, and food is great. Let's see, service is poor, service is poor, service is poor, and poor, we said that 0.2, and the rule says, and food is great. So food is great, it means 0.6 and 0.2. So minimum of them 0.2, and the tip is cheap. So tip we know tip is cheap, 0.5%. Tip is average, 13%. Tip is generous, highest percentage, 25. So 0.2 multiplied by point, 0.2 multiplied by 0.25. That's for the third rule. This is second rule. This is first rule. Over the sum of the weighted average, which is 0.6, 0.4, 0.2. And here the tips is 17.67%. Now, cases, you can see the differences. In the first case, we got this one. The second case, we got this one. 3 rules. And now what analysis we can conclude is that the additional of Rule 3 introduces the influence of poor service, even though its membership is relatively small, 0.2. But again, it reduces the final tip from 20.2 to 17.67 because that poor service made the tip get less. So sensitivity to overlapping, fuzzy sets, smooth decision, avoid abrupt changes, and provide gradual transition between decision. So problems of fuzzy logic, not easy to tune membership functions, might not be a good choice to be adapted for larger problem in terms of many outputs or many inputs. So this fuzzy logic cannot be a good solution. Deals with imprecision and vagueness. In conclusion, these are very, very good. Fuzzy logic is very good. It has a lot of good things, simple, no great math in it, but it has some problems. No small input changes make small output changes, and overlap membership functions create smooth transition. No rapid switching because it's everything to a degree is going. So fuzzy logic can be good for those systems that control is essential in those systems. In conclusion, it's a good way when your application deals with vagueness, imprecision, imprecise things, and usually we use it for linguistic variables, so things that can describe by linguistic and cannot be exactly represented. We have fuzzy membership sets, and we have fuzzy linguistic variables, and we have connectors and an OR, and we have fuzzy control. Thank you very much for listening to this simple tutorial. I hope we will have more tutorials on advanced level of fuzzy logic. Thank you very much. Stay tuned.